talking about rotational motion, what is a measure of an object's inertia? What limits an object's acceleration? Mass. So remember inertia. So we're going to start with rotational inertia before we go into circular motion. Inertia is an object's resistance to changes in motion. And what direction does an object always want to move? Right. Wants to keep doing what it was doing straight, right? And that is the mass. What do you think rotational inertia is going to be then? Resistance to changes in what?
Yeah.
That's really still linear.
Velocity over muscle.
Rotation.
Wow. Oh, yeah.
This is often called moment of inertia. Our physics book here calls it rotational inertia. A lot of physics books will call it moment of inertia. If you become an engineer, which I think some of you probably will end up being that, they'll often turn it into moment. The moment, which is just short for moment of inertia. Okay? This is affected by two things. One of which is mass. Anybody know what the other one might possibly be? When I give you some examples, you'll actually know this. It's the distance the mass is from the center of rotation. So, who here has ever tried to spin with a barbell in the weight room? So if you pick up the 35-pound dumbbell or the 45-pound and you try to twist it versus the 45-pound barbell, which one has that weight further from the center of rotation? The barbell. Which one is easier to spin? The dumbbell, because that weight is closer. Okay? A solid thing is going to be less difficult than a rotating thing. Okay? We'll come back to this and I'm going to show you a video on this at the end of the day. Okay? So everybody got that down? Anybody know what torque is?
That's some good resistance for the
No.
force over time, rotational.
It's rotational force.
Now,
Okay? Essentially, that's the simple way of putting it. It's the rotational force. So when you take off a bolt, Everybody here like loosened a bolt before in their life. You use a wrench, right? Maybe you use your fingers. So, torque is equal to force times the distance at which that force is applied. We're going to assume, for simplicity's sake in this class, that we apply the force at a 90 degree. We push against the wrench, we don't push angled on the wrench. Okay? What do you do when you can't get the bolt off? Okay, one option is twist harder. What's the other option? Get a longer wrench. So Curtis is using heat to try to reduce friction. That tries to reduce the torque needed. But first you probably got a longer wrench, right? So you can use oils. What are those doing? They're trying to reduce the amount of friction between the bolt and the nuts or the block that it's in. Okay. Heat is trying to use thermal expansion. That's coming later. But for simplicity, you either increase the force or you increase the distance by using a longer wrench. Okay? Torque is usually, I think it's the lowercase tau. The Greek letter. Torque is also equal to I alpha, if I'm remembering correctly. Yeah. It's like, I haven't looked, that's not in this book. I stands for rotational inertia or moment of inertia. Alpha stands for angular acceleration or rotational acceleration. Okay, we are not really going to go very deep into this, but several of you are going to go on to take much more mathematical physics like 201 and 202. Angular means rotational, so angular acceleration. I'll give you a few more variables that are coming up. Omega is angular velocity.
Up is angular acceleration.
Angular acceleration. So notice that that's very much like mass times acceleration, except it's the rotational inertia. Yeah, it's Greek letter omega. Okay. Welcome to physics. We're going to be using lots of Greek. Physics is kind of a good mix.
Yeah.
I was like, we use and unfortunately, there's certain letters that really are context dependent, and they can mean four different things.
Is that gamma?
What?
Or velocity?
Omega. It's like a curved in W kind of shape. Okay. So, does that kind of make sense for the introduction to torque? Now let's start talking about objects moving in a circle. So here I've got a set of washers on a string. Thank you. So, what is causing these washers to spin in a circle? No, I am not. I'm not touching the washers. The string. So, the string is providing inward force, correct? Why aren't they being pulled in then?
Because the washers are applying outward force.
Because they're heavy. Ooh. The washers are not actually applying any force, but it's often called a force. Okay? What direction do the washers want to go? They want to go straight. So if I release them and throw them into the floor, they go in a straight line, don't they? What property says they want to go straight? Inertia. Thank you. So, inertia makes objects want to go straight. You will sometimes hear this referred to as the centrifugal force or the fictitious force. I don't like the word the centrifugal force. It sounds like a force. I don't mind the fictitious force. Fictitious. I'm not sure if that's spelled right. So I don't mind calling it the fictitious force so much because it's not actually a force. Okay? You accelerate around a corner too fast in your car and you push towards the outside wall. You feel like force is acting on you. What you're actually feeling is the acceleration. Why is it accelerating when we go around a corner? We're changing what? Direction, which means we're changing velocity. Okay, we feel that acceleration. We actually feel what's called the fictitious force. The centripetal force, on the other hand, is the center-seeking force. When you go around the corner in a car, what provides your centripetal force?
Wheel.
For the car, the friction of the wheels to the ground. For you in the car seat, the seat belt and the friction between you and the seat. Okay? What is providing the centripetal force here? The string. So this is a tension force, right? There is no specific center-seeking force. It's just a general force that seeks towards the center. Okay? That's holding something, making it go around in a corner. So we've done lots of free body diagrams, much to your chagrin, right? Okay? So as we've done these, you you calculated net force, right? Oh wait, center seeking.
Hmm. And then
Neither did I.
centrifugal is
That's kind of the outward feeling thing that's not actually a force.
I always call it a pseudo force when I discuss it. I always say pseudo.
Pseudo force?
Yeah.
Yeah. Pseudo force.
I can say centrifugal and I just say pseudo force.
Yeah, I like to call it fictitious force.
Because you have, an acceleration pseudo force, and you
Mhm.
accelerate forward, you feel thrown back.
You
If you're
feel-
not being thrown back, you're being run into by a vehicle.
Yeah. The force is the seat actually pushing on you. This is this is always the centripetal force is always a net force. Okay? It's caused by something else. Yes, I can. We're in this class, we're going to focus on constant angular velocities, not accelerating ones, where it's picking up how fast it's spinning. What do you think the most common unit that's used in life for an angular velocity, or how fast is this spinning?
rotation.
Revolutions per minute. RPMs is revolutions or rotations means the same thing. Per minute. In physics, we often measure it in radians per second. Now, some of you are far enough in math to know what a radian is. Should you know what that is? I think I talked about it for 3 minutes when you were in integrated two. So, so probably not. You've learned that in pre-calc. Okay. And we haven't gotten that far in pre-calc. So, for the most part, no, you don't know what radians are. Radians are another way of measuring angles. They work better than degrees for a lot of the math. So, I've told my calculus class that what do you do all your calculus in? Radians. Why? The formulas, there's variations on the formulas for degrees, but they're so much harder. So we just work in radians. It's this interesting unitless measure for a circle. Okay. Again, you don't really need to focus on that, but it's basically like angle per second that's covered is what we often do in physics to measure rotational speed. And if it's angle per second, you'd have angle per second, or angle per second squared for angular acceleration. That kind of makes sense?
I hate to interrupt you, but I was gonna take off. What will you get
Okay.
as an assignment typically for these things?
This would just be,
Seven.
yeah, some questions at the end.
Okay, that's good.
Okay,
Thanks, everybody.
thank you.
For me hanging out here. Fun.
Yeah. So we've talked about angular speed. How many rotations is it making per second or per minute?
At least one.
Probably 2 maybe here as I'm spinning this. But what if I want to know how fast is it going if I took it in a straight line?
You could roll it in straight.
I could.
Could you?
And that's going to give me what's called the tangential velocity. Okay. That kind of makes sense on tangential. So that means it's straight. Basically, I've got this motion in a circle. Do you guys know tangent to a circle is like this off the side? So we can represent tangential velocity with a straight line vector. Does that make sense? It's pretty simple thing, straight line vector. This thing's moving in a circle. How fast is it moving if it's straight line? Where does tangential velocity become super useful for us? And everybody used it this morning, sort of. When you drove to school. The wheels on the car. The tangential.
Oh,
How dare you not drive a car to school?
that's.
The tangential velocity of your wheels is how fast you go. Okay. Anybody know how a speedometer works?
It looks for speeds.
It measures the rotational speed off the transmission of the car, and it uses essentially, so it's got a rotating thing that measures rotational speed. It knows your tire size. Anybody ever changed tire size on their car? Like gotten bigger wheels? Your speedometer ends up being off. Because, well, what happens? I've increased the radius. It's reading a rotational speed going to that wheel, right? How much ground do I cover if I increase the radius? More. So all of a sudden I'm going faster than my speedometer reads.
It's most muscle cars come with like bigger rear tires than front tires. How does that work?
If they're calibrated, so if the car was designed to have that size, it's designed for those tires. It doesn't care what the front ones do. Okay? Because a muscle car, you're talking about a rear wheel drive car. Yeah, you have to be careful of that.
See, officer, I was speeding. I just didn't calibrate my speedometer.
Then your speeding is based on what the officer reads, not what your speedometer says.
So I in fact was not going 120 miles per hour.
That's not how it works.
It's 200.
Yeah, that's So I'm guessing if you have a self-driving car, Noah and Izzy, I'm guessing there's a way that you can reprogram, say, a Tesla for different tires, or at least a Tesla truck.
So hypothetically, if you know someone who has a Tesla,
That's illegal for your mechanic. Like, I specifically almost, Costco almost wouldn't sell me tires because my yellow car out there, my dad got different rims, and there's only a certain legal size of tires that fit in the wheel wells.
so what you're
Yes,
saying
it's
is,
illegal for them to sell you tires that don't fit on your car.
so what you're saying is hypothetically, find someone who has a Tesla and then reprogram
Anyways.
it on.
No,
Funny little friend.
Tesla equals straight across. It's good.
And so on the outside,
The red one?
those well, maybe it would not hit, but I think usually they're inside a little bit.
I see.
There's a lot of legal restrictions to keep people from doing things that they don't want, or to keep a company from selling you what you don't actually want because you didn't know the unintended consequences. Okay. Does that kind of make sense with circular motion? Okay, there's a very interesting thing in this book about train cars. Okay. So everybody's what?
The wheels, I'm assuming.
Yes, the wheels. So when you go around a corner, I'm going to share something different here for a second. So I need to pull this up.
Me.
I don't want whiteboards. So anybody know how a differential in a car works or why it works? They both work the same, but rear is probably the easier one to think about.
What makes it?
Isn't that what allows the car to dip in order to drive?
The differential. So when you take your car tires around a corner, do your tires travel the same distance? So do they have, can they go at the same speed if you want to actually make the corner? No. So they have to be able to go at a different speed because the outside of the corner is a further distance than the inside. Correct? Who's seen those big things on the back of a truck axle? You'll see the big thing, they call it the mushroom. Kind of in the middle of the axle. Inside of that is what's called a differential. Okay? This is a brilliant piece of engineering. If you have a front wheel drive car, there's one in the transmission under the hood.
It's very, very nice to have, but it's hard to replace.
It is harder to change, yes. They're easier to work on rear wheel drive cars. So in this right here, everybody see what I've got here? That drive shaft is coming from the engine. These go out to the wheels. Okay? In them, you have this gear that's turning. This red part is attached to that gear, which twists this whole differential. So when it twists, it spins, which spins your wheels. However, if one of the wheels is going a further distance, it can shift on these gears that are within the red thing. Okay? And as it shifts on those gears, it allows them to spin at a different rate. Anybody ever had a car hop around a little bit when you put it in four-wheel drive? Where you're like going around a corner in four-wheel drive and your car's like bouncing a little bit? That will happen if you don't have a differential between your front and back wheels, which a lot of cars don't. All-wheel drive cars have differentials in the front, back, and between front to back. A four-wheel drive truck usually doesn't, so you don't turn on the four-wheel drive unless the roads are slippery or you're on dirt where the tires can slip. Okay? So, if you look in your book on page 156, they're going to talk about how you do this with train wheels. Hold on, I'll open this up. I have a scan of this. So, trains don't have differentials, they have a solid axle. Trucks do not have a solid axle, they have a solid axle outside of a axle that actually spins it. You've got an axle inside of something that's solid. Okay?
Oh.
Hold on.
I really. Oh, you fixed it.
Yeah. This is struggling today with basic tasks.
Oh.
Probably needs to be restarted.
No, it's just the way these those the trade cards so can't do because center. So if it doesn't come in.
Okay,
What do you need?
train car. Notice the shape of those train wheels. They are a piece of a cone. So if you extended them, they'd be like a cone that meets here, which means the two edges have different radiuses, don't they? Who here's ever played with a model train? Do they fit tightly on the tracks? No, there's a little bit of loose weight, and that's because actually trains have a little bit of looseness. So they make the wheels wide enough so that if you look here, when you're going around the outside of a corner, notice this side is pushed against here, but I've got a little gap right here. Okay? So the inside corner is on the inside of the cone. It's a smaller radius. The outside wheel is on the big part of the cone, larger radius covering more distance, allowing the outer wheel to go further than the inner wheel. Does that make sense? So we've got interesting piece of engineering here. In order to go around a corner on a train, you have a difference in radius on the wheels. When you're going straight, it's just going to center out so they're the same. And the car just shifts side to side on the track as you go. Okay? That makes sense. Kind of a weird, interesting, different kind of way of looking at this. Okay? That's how train cars work. That's the circular motion here.
Is your recording still paused?
No. Okay. So now we're going to talk about how to calculate centripetal force. Okay? Centripetal force here has a pretty easy formula. F equals m. You'll often see it just as mv, but I'm going to put it as tangential velocity to be specific over the radius. So the force needed by this string is equal to the mass of the washers
Oh,
times the tangential velocity of them, so the straight line velocity, divided by the radius of rotation.
I'm assuming both of those are squared.
No, just VT is squared. So if I shorten my radius, do I need as much force? No, less force is needed. So we said the tires make the car turn, right? How do you drift a car?
depends on how you want it, you can just. You can.
Accelerate,
Give it
make
E-brake,
turn.
right?
Hold the A button.
What's the physics behind how you drift a car? So when you drift a car, your car is skidding outward, right?
You're increasing and shortening the duration of your turn.
So your car's skidding outward when you're drifting a car. Everybody paying attention here. So remember that the static friction is always greater than the kinetic. If your car is driving down the road, are you using static or kinetic? Static between your wheels and the ground because your wheels are not slipping. When you start drifting, your wheels start slipping. Okay, you're letting your car slide on the wheels. That's kinetic. So you've immediately reduced your friction force. What force causes you to turn? Friction. If you turn at a sharp enough radius that your centripetal force is less, actually, this is adversely. So as I come in, the centripetal force gets greater than as I'm out further. Okay? So I'm dividing by radius. If I make my corner too tight, I divide by a smaller thing. I need more force. Well, if that's more force than the friction can give, what starts happening? You start sliding. Okay, that was one of the problems on your forces quiz. It asked you what was the maximum you'd pull. As soon as you become greater than the kinetic friction force, or the static friction force, it moves. And it becomes kinetic friction, so it accelerates. Okay? So as soon as this becomes more than the friction can provide, I need more centripetal than the friction can provide. It becomes kinetic friction, starts sliding out, going more straight, increasing the radius of corner. Eventually, your radius becomes great enough that kinetic friction stops you from slipping anymore, and you're back to static friction. And your drift is over. Okay. Yes, there are lots of ways you can actually make the car drift, but that's the physics that's actually happening. Okay. So if I should someday, ask you how do you make a car drift, or how do you make the car actually drift in Mario Kart, you need to explain the physics behind it. There might be a question on an extra credit question on the next test, but explaining drifting in Mario Kart.
Oh, interesting.
Alex, no.
Gonna write a separate like essay on that one. Just ones and zeros.
They actually do a good job of making it pretty realistic with a lot of the physics in the newer ones.
Units for Mario Kart. It's gonna be eighth as that one's the most correct.
So,
Mario Kart has this low unit measure. What is 7?
okay, last thing we're going to talk about. Simulated gravity. Oops. Anybody know how to do simulated gravity? So the first question becomes, what makes you feel like gravity is acting on you?
Density. Mass.
The normal force. I feel like gravity is acting on me because I've got a chair pushing up on me. If you're standing, it's because the floor is pushing up on you. Anybody ever taken like a long fall and felt weightless?
No.
Like if you jump off a big high dive or I went cliff jumping when I was younger. You you start to feel you start to feel weightless, even though you're falling towards the earth.
Yeah.
So the what we experience as gravity is actually the normal force. So if I rotate an object, you look at the book, they show this with a ladybug on the outside of a wheel. But if I've got a space station here and I rotate it here, the outside wall becomes my ground. If I rotate it at the right speed, the normal force is what's going to cause me to rotate, right? Instead of going in a straight line. So it's going to feel like gravity is acting on me because I will be against the outside wall, with the normal force causing me to spin instead of keep going in a straight line, and that's going to feel like gravity. Okay? Most space movies, if you watch them simulate gravity, they actually do make it rotate. Okay? Back to rotational inertia. Who here's ever walked a balance beam? Or a tightrope? What does a tightrope walker usually carry? Big long pole. Okay? Why do they carry a long pole?
Increases their radius.
It increases their rotational inertia because they get weight out at the end of the pole, right? You don't actually fall off a tightrope wire, you rotate on and off. Okay? So you're rotating off. If you can increase your rotational inertia, it takes you being more out of balance to rotate off. Okay, one more thing. Center of mass. Where's the center of mass of these washers?
Center.
In the center, in the hole, right? There's currently nothing, there's no mass where the center of mass is. But if I throw them, their center of mass will follow a nice orbit. If I throw a pen, if I throw it with the direction going through the center of mass, and all of you that can throw a football or a baseball do this. You throw it through the center of mass. It kind of falls decently, correct? However, if I throw it not through the center of mass, my force doesn't go through the center of mass, it goes through the end.
And it spins.
That's essentially putting a torque on it because center of rotation is here. I've got a distance. It's going to spin. So, who here knows what a wounded duck throw at the football is?
Not
Wounded duck.
No.
How do you not know this, Curtis? It's a wobbly football. It's not a good spiral. Means you did not throw the force, your direction of your force from your hand, didn't go through the center of mass of that ball. Okay?
I don't know that. I don't do that.
You've never done that?
He's just so good that he's never messed up.
Okay. So, how do I keep something from toppling over like this pen? When is it going to topple? When the mass goes over the edge or what's called the support base. So if the center of mass is above the support base being the bottom, it will balance. If the center of mass is not above the bottom,
Anyway,
the center of mass goes outside of the support base, it topples over. This marker is fairly tippy. What's the support base of the chair you're sitting on?
the legs.
It's actually the entire area under the legs. Okay? Yeah, so as long as the center of mass of you and the chair combined is anywhere above the four legs, it will stay balanced.
I have two of them, so
It's anywhere above the four legs.
I'm on one.
Even if you're on, so if you're on one, if you're on two, you need your center of mass to be above those two. Okay? Now, most of you guys are supporting yourself with a hand on the table. Okay?
Immediately gonna break my hand. It's absolutely.
So, is it hard to balance perfectly on two legs of your chair? If you got feet on the ground and you're leaning back on two legs of your chair, it's two legs of your chair and your feet.
No.
Okay? But notice it's a little difficult to balance without that. Okay? Center of mass. Very important. That makes sense. That's the end of today's lesson.